I will try. I think pretty much everyone has turned in the first homework. I will try, no promises, to get those graded. Well, they shouldn't be difficult to grade anyway. There's not many problems. By sometime like early next week, like next class. And then I've put up the third homework that's going to be due not for a while, like on the 15th, because on February 13th, that's Tuesday, that's the Mardi Gras break. So we won't meet then. So try to have your brain cells back in order for the following Thursday at least. Okay. Now, it's fun to talk to people elsewhere, but it just blows their mind that we have a Mardi Gras break. About 1 year, they only gave the Tuesday off. Like, I actually expected people to show up on Monday, and that didn't go well. Okay, so, but since you have homework 2 going on, I'm going to give a couple pointers about a couple problems in that assignment. Okay. So this is in section 3.2. So wonderful problems there. I think it's the very first one, number 4. That problem asks to show, or prove some of the properties of lower and upper triangular matrices. Like a product of 2 upper triangular matrices is the same triangularity and same for an inverse. So what do you want to use for that is a generic formula for matrix multiplication. Just the sort of thing that you learned in your first year algebra course and therefore had plenty of opportunity to forget. So that formula is, so if 2 matrices A times B and you get C, then the formula is entries of a product C. And we'll assume that everything here is n by n as usual. So each entry is a sum. So the ij entry, we're going to have an entry of A and an entry of B. And watch what I do with the indices. So the index, the row index, is the first index of A. The column index is the second index of B. And then the index from a summation, K, is the second index of A and the first index of B. So that index goes here and here. So if you have, for instance, suppose A and B are both upper triangular, but you want to show that C is upper triangular, and keep in mind, what you'll need to use is the definitions of triangularity. Okay, and that is for upper, Aij is equal to 0 if I is greater than j, and for lower triangular, Aij is equal to 0 if I is less than j. So to give you a template, if you will, like let's suppose that A and B are upper triangular. You want to prove that C is upper triangular. So what you can do is you can assume I is greater than j, and then show that what you get has to be 0, because so if you assume that I is greater than j, also since these are upper triangular, so for instance, this equals 0 if I is greater than k, and then this equals 0 if k is greater than j, but I is greater than j. And all of this is only applies for the upper triangular case. It would all be backwards if it was lower triangular. So these are the kind of things that you would use. So I've given you actually, whoever it may not seem like it, I've given you one heck of a start on this. And see if you can finish off a bit to show that it has to be 0. Now, if you're having trouble seeing it, one good thing to try would be try an example. Like just make up a 3x3 case, just with any numbers or even x's. I do a lot of examples where I have part of the matrix non-zero. I don't really care what the non-zero entries are, so I just put x's and see, well, what has to be zero, what has to be non-zero, and that can help you see why it actually works. Now, that's for a product of triangular matrices. What about the other property? To show the inverse of a, for instance, upper triangular matrix is upper triangular. So what you do is you assume A times X is equal to identity. So A is known to be upper triangular. And therefore you show that the entries of X, which you don't know yet, so X is A inverse. So you assume you assume that A is upper triangular, show that in order to get a product of identity, then X itself, the inverse, has to be upper triangular also. And the way to do that is, so for upper triangular, you examine the first column. So if you consider computing the first column of this product, so what's happening? To compute the first column of a result, you're going across every row of A and down only the first column of X to produce the first column of identity. So you end up showing that x12, that's not 1, 2, 2, 1, x3, 1 up to xn1 all have to be equal to 0 in order to get this, because identity is a matrix that has all ones on the diagonal and everything else is 0. Given the fact that A is upper triangular, therefore you have this property applying. Show that corresponding entries of X have to be 0 also. Otherwise, there's no way you'll get identity. Okay, so no, it's not going to be an easy problem, but get on it. See how far you can take it, and then you can ask you questions about it as when you get stuck. Any questions now?
No, not planning on getting stuck.
Okay.
The homework is tomorrow, right?
What?
The homework?
This isn't, no.
The quiz.
Yeah, the quiz.
The quiz is due tomorrow. Yeah, this is not due until Tuesday. Okay. All right, so that's about the first problem. And the other hint I want to give is about I think it's the last problem. And so this is from the problems in the book. Okay. All right. So exploration 20. Now, I only gave 8 problems out of the section, so I skipped a lot. So this is where you write a Matlab function. X is equal to solve AXB given inputs A and B. So this is going to call 3 functions of yours that all came from previous problems. Gauss Elimination that computes the LU factorization. You actually, in the earlier problem in this homework, you need to modify the one you did from homework 1. So you're going to call that, and then you're also going to call a function for forward substitution that you write earlier in this assignment. So A gets passed to Gauss elimination, which is meant to produce a matrix that I call LU. It's one matrix, but it has both L and U in it, because U goes in the upper triangular part, and then the multipliers go in the lower triangular part. So you have everything. So then, forward substitution. Wait, so I need to check something about this problem. For using pivoting. Okay. Whoops. Okay. Okay, so actually, this will need to return two outputs. LU and P will indicate what row interchanges were made. I'm going to talk about that in a little bit. So forward substitution will be used with L. Now, here's what you can do, though, is forward substitution will be made for a unit lower triangular matrix. So all you need is the stuff in the lower triangle. So you can actually pass LU to forward substitution. And PB, which would be the permuted version of B. Now, mathematically, that's how I would write it. But as far as code goes, I'll talk about that in just a moment. But the point is, row interchanges have to be applied to P. So I want to emphasize here, this is not literally what you will type. Matlab. I will explain this in a moment, I promise. Okay, but someone's going to do that anyway, so don't be that student. Okay. And then you get the result of y, because you're solving Ly equals b, or rather PB. Okay. And then you have your back substitution function, which was from homework 1. And it's for solving ux is equal to y. So you pass the appropriate input arguments, and then the output of that is your solution, x. So solving xb doesn't really do anything on its own, except pass a buck to these three functions. So it's like a manager, if you will. Just has to be sort of what is the right input of each function. What do I do with the output? And that's it. Okay. All right. Now, as far as because this Gauss elimination function, what do you do in earlier problems, does not account for pivoting. So I need to talk about that. Okay. So for Gauss elimination, how to do pivoting. Okay. So, because you have your loop, your outermost loop, j going from 1 to n minus 1, and you're looking for, within that column, for the right element to, right row to interchange of row j, if any. So, what you need to examine is a portion of A that would be rows j through n, column j. So that's the relevant portion of a column you need to look at. And Matlab has a function that's just called max. It returns a maximum element. But remember, we want the maximum in absolute value. So Matlab has a function for that too. Absolute value, ABS for absolute value. So those two functions, you'll need to figure out what is the largest element to work with. now, think about the maximum function, how you can use that. Let's see. Actually, I want to be absolutely sure about this before I tell you. Come on. Okay. Now, here's how you can. There's different ways to use, well, many MATLAB functions, but here are different ways to use max. So, and you can see this in the help page for max, which I would encourage you to look at. So, if you pass into max a vector, I'll call it x, that just gives you whatever is the largest element. But here, you're trying to figure out where the maximum is. You need to know where it is. So, like, which row does it occur in? So you know which rows to interchange. So that's not the best usage in your case. I'm going to add a second output. I'll call it ind for index. So whatever you pass in here to take the maximum of, this will tell you the actual maximum value, which is not really what you care about. This is what you care about. What index, or I should say indices, at which the maximum value occurred. And I say indices because what if there's a tie? It's going to give you all of them. So in your case, you can use any maximum. So you can use like ind1, like the first place where it found a match. That would work just fine. So now you know which element of this, where the largest element was found. Now, here's a big gotcha though, because so the swap, like row I, let's see, I'll call it row P. So wherever you found the maximum, you'll swap row P and row J. The easiest way to do that is using MATLAB's indexing features. So you can say so you can specify a row vector of any valid indices at all. And so you can say row P and J, and the colon means all columns. So this refers to the entire rows, P and J. So you want to fill in rows P and J with rows J and P, swapped. So you can just do that. So switching the indices. So this will extract rows J and P in that order and stuff them into rows P and J in that order. That will swap the rows. So you don't need to use a loop or anything to do that. Now, okay, so I need to point out the gotcha. In doing this maximum thing, I keep in mind what I'm writing here, this is generic usage. Okay? Now this is used on, so this is going to be part of a column. of A, not the whole column. The index here is from 1 up to the length of x, whatever you pass in. So for example, suppose I'm on column 3. So I'm extracting columns, so suppose I have a 10 by 10 matrix. I'm working on column 3. So I have rows 3 through 10 of column 3. That's a vector of length 8. Mm-hmm. So let's suppose that the element in row 9 is the largest. So I want to swap rows 3 and 9. Well, row 9 it's in the 9th row of the entire column. It's only in the 7th row of this, because you're only taking part of a column. So what's going to happen is I call maximum on this. It's going to give me the maximum value, and the index it will return is not 9, it's 7. I have to correct the index. So whatever index you get out of this, you have to adjust it to account for the fact that you only took a part of a column. Now, for a first column, you don't have to adjust it at all. But for every other column, you have to adjust it. And you can figure out, in terms of J, what the adjustment should be. Like the example I just gave you. Third column, it was off by 2. Extrapolate from there. So you adjust index based on what column you were working on to get to the actual index P of a row you want to swap. So you can go ahead and do a swap, and that's the only change that needs to be made to Gauss elimination to make that work. But then, okay. Now, what about storing the permutations, though? I talked about that a little bit last time, but I need to say a little bit more. But any questions about this? And I'm trying to leave just enough breadcrumbs, but no more. So. Okay. So once you've decided, okay, I'm going to swap these rows, and you go ahead and do that, you need to create a record of that to pass back, because you need to know what all the permutations were to carry out, so you know what to carry out forward substitution on. I just realized I'm spending way too much time talking about this, because I actually meant to material today. Well, we'll see. All right, here's what you can do. To store permutations, we're not going to create a whole permutation matrix. That's a waste of storage. We're going to make a vector. Okay, so initially, before you start Gauss elimination, P, we'll just let it be the indices 1 to n. So the row vector has 1, 2, 3, 4, 5, all the way up to n. Okay. I just really didn't use P for row I'm going to swap, but okay. This is a big, exaggerated case P. So I want to stay consistent with my other notation. So to swap rows J and little bitty lowercase p. Okay. Hopefully those look different enough. What you can do is, when you're swapping those rows in A, you go ahead and do that, just like I described. You also update the vector capital P in the same way. Okay. So by the time Gauss elimination is done, this vector capital P will have all the row interchanges performed on it. So now, whatever indices you have from 1 to n, those will be the order in which a row should be. So then later, when you do forward substitution, you'll have your matrix LU, because it's okay to pass all of LU even though U is in it, because forward substitution will only access the lower triangle, which has the correct elements in it. So you can pass this to forward substitution and backward substitution, because backward substitution will only access the upper triangle. So this is the only matrix you'll actually work with. So I mentioned earlier when I described forward substitution that what I had earlier is not what you type. This is what you type. You take B, your vector B, and then you pass your vector of permuted indices as the indices to B. What this does is this scrambles the elements of B according to how the indices in P are scrambled. So by working with a vector, it's very easy to work with this permutation of indices later on. So this accomplishes the same effect as if you were to make a permutation matrix and multiply by that, but this is a whole lot more efficient. Okay. All right, so that is the excessively long, ugly story of how pivoting is handled. So any questions about that? Okay. All right. Now, all right, so that's all I have to say about the homework at this time. As for what I actually intend to cover today, before I can cover it, I have to, there's going to be a couple instances of things you're supposed to learn in your first linear algebra course, but our version of that linear algebra course tends not to cover. So you're going to get it now. Because it had to be everybody's linear algebra savior. Okay. This is about what are called norms. Now, we deal with vectors and matrices all the time, but often we need to describe the magnitude of a vector matrix using just a single number. So this is what norms are for. They're used to describe the magnitude of a vector or matrix. Now, one of these norms you actually have seen in calculus, or maybe your first linear algebra course, where you take a vector and you take the sum of squares of the entries and then take a square root. So that's Euclidean length. That is an example of a vector norm. So I'm going to talk about vector norms first, the easier kind, and then matrix norms on top of that. Now, properties of that, and actually these are, in the book, these are covered in Appendix B. There's a whole section on them that might be good to look at. Okay. Now, here are the properties that a vector norm has to have. So first, I use a double bar. So it's kind of like absolute value, but you have double bars to indicate a norm of a vector or matrix. So the norm of a vector x has to be non-negative, because it makes no sense for magnitude to be a negative number. Also, the only time that a norm of a vector is 0 is if the vector itself is the 0 vector. Again, it's just the only thing that makes sense. Second, because we're talking about like length, if you scale a vector by a constant factor of c, then that will scale the norm by the absolute value. So for instance, you double the length of a vector, that would double its magnitude. If you negate a vector, that should not change its magnitude, it only changes the direction, and so on. And finally, this you know as the triangle inequality, certainly for absolute value. It applies to norms also. And it just says that the norm of a sum of vectors is less or equal to the sum of the norms. Okay. And really, the absolute value of the number is, you can think of it as the simplest norm of all. Okay. So, here's some specific norms of interest. Well, first, a category that are called P norms. So indicated by the subscript P. So P is going to be a number. So what you do is you take the sum of all the entries, absolute value, raised to the P power, sum them all up, and then you raise the sum to the 1 over P power. So you've already are familiar with this in the case of P equals 2. So that's like the Euclidean length of a vector. So for instance, P equals 1, we have a 1 norm, and that's just the sum of the absolute values of all the entries. P equals 2, so that's the 2 norm, the one you're most familiar with. So that would be the square root of the sum of squares. Now, there's another way of writing this that's going to be useful to us now and then. And that is the square root of x transpose x, assuming that x is a column vector. Because if you take a column vector and then it just transposes a row vector, if you multiply them, it's a dot product with itself. So that would have the same effect if x is real, which that's all we're going to deal with. But I have to say that, otherwise someone might point out that I'm wrong in the case where x is complex. Okay, so don't even. Okay. And then the other interesting case is p equal to infinity. So like if you take the limit of this, the higher p gets, the more the largest element of x gets emphasized in the norm. So the infinity norm, also known as the maximum norm, is just the absolute value of the largest element. Okay, so a particularly easy one to compute. You're not really having to compute anything. You're just comparing. Okay.
What is the square root of x?
X transpose x. Yeah, it's an uppercase T. Okay. For the 2 norm, there's one useful inequality that you might have seen in calculus. Cauchy-Schwarz inequality. That says that the dot product or inner product of 2 vectors, x and y, is less than or equal to the product of their 2 norms. So that's something that comes in handy now and then for certain proofs. Okay. Okay, so any questions about vector norms before I talk about matrix norms? Can anyone see this okay? Or if something is not legible, please let me know. I'm also looking at my screen for recording. It's like, whoever has to watch this video, I feel sorry for them. Sorry, Teresa, Treasure, and Layla, and whoever else I'm forgetting. Oh, Kelsey, too. Okay. All right, so now, no, dang it. Sorry, I just got a very frustrating message.
It wasn't from me.
All right, matrix norms are built on vector norms. Now they have the same properties as vector norms, as in they have to be non-negative. A norm of matrix is only 0 if a matrix is 0. Scaling matrix scales a norm. Triangle inequality, all that's the same. I'm not going to write it down again. Except there's one additional property that matrix norms have, and that is the matrix norm of a product is less than or equal to the product of the norms. So that's going to be useful to us. Okay. All right. Now, so how we define a matrix norm? They are induced, most of them, by a vector norm. So in fact, we have the same names as the corresponding vector norm. It's clear from context, but we're talking about the vector or matrix. Okay. So what you do is the P norm of a matrix for whatever value of P is the maximum of the vector norm, same vector norm, of A times X, where X is any vector that's a unit vector in that norm. So you can think of a mixed norm as it's the largest possible amplification of a vector that it could possibly give. But this is not a very practical definition at all. So I can give you practical definitions for certain matrix norms. So the one norm of a matrix turns out to be the maximum, and I'm going to assume that A is m by n. Does not have to be a square matrix. So what we do for the one norm is I can interpret this for you. It's the maximum column sum. So if you take the absolute value of all the entries, you add up all the entries in each column, and so you get a column sum. The largest of those column sums is the one norm. The infinity norm is very similar. You take the largest row sum. So if I give you a matrix, it's actually quite easy to compute its one norm or infinity norm.
What does the m by n go to? Number 1 or number 2?
Both. Yeah, any example I give in this section. So you could say that the infinity norm of A is the same as the one norm of A transpose. That reverses the sense of rows and columns. Now, unfortunately, whereas vector norms, any vector norm I give you, it's easy to grind out on a calculator or Matlab. Matrix norms, not so much. Now, those two are straightforward, but not the two norm. The matrix 2 norm, by the way, there is a norm function in Matlab, and Matlab by default will use a 2 norm, but you can, if you want to specify a different norm, you can. Now, this is going to be the maximum over all unit vectors of A times X. Now, I'm going to write that a little differently. It's also what is called the supremum or over all non-zero vectors x of 2 norm of ax over 2 norm of x. This is said if we now assume that x is a unit vector, but denominator goes away. And I have to say suprema, which means it's the least upper bound. So those of you who haven't taken real analysis yet, you'll deal with that term then. It's just because I'm not allowed to say maximum in this case. But it almost has exactly the same meaning. Now, it turns out I can come up with a formula for this. It just takes a little bit of, okay, karate me, because I'm using my own computer. So I'm going to find a maximum of this to figure out 2 norm. So I'm just taking this to get rid of square root. So I have that divided by transpose x. So that's why I gave a definition of the vector 2 norm earlier, because it comes in handy here. Now, using the properties of a transpose, that would be x transpose A x transpose. So what I would do, there's a function of n variables, all the components of x. So I would use multivariable calculus. Now, when you're finding a maximum or minimum of a function, take a derivative and set it equal to 0. Now, for multivariable calculus, similar idea, take a gradient, which is all the partial derivatives, and set all of them equal to 0. Now, I'm going to do a lot of shortcutting here because of time. So you can take my word for it, or I think it's worked out somewhere in the book. For this is a quotient. So I'm going to use the gradient of g. I need the quotient rule for that because it's quotient. That's multivariable, single variable, makes no difference. And that would be the bottom function times the gradient of the top minus the top function times the gradient of the bottom over the bottom squared. Now, so that would be, you can think of this, if this was one variable, that would be a squared x squared. The derivative of that with respect to x is 2a squared x. So it's going to be similar to that. It's going to be 2a transpose ax. And then over here we have minus x transpose a transpose ax squared. The derivative of that is 2x. So in fact, that's literally the gradient of x transpose x squared. And I want this to be equal to 0. So I'm going to factor out what I can. I can factor out 2 over x transpose x. So we're going to forget about that. And what's left is, from this part, a transpose ax minus, and simplifying the rest of this, I'm going to have x transpose ax over x transpose x, that's a number, times x. And I want this to be equal to 0. Now, is actually my original function, g of x. But notice what I need to have is this matrix times x minus this number times x must be equal to 0. And what that means is ax is equal to lambda x. Lambda is g of x. And can anyone tell me who's seen more linear algebra than the average bear what kind of vector x must be? It is an Eigen Vector. And lambda is called what?
An eigenvalue.
Eigenvalue. Now this is something that is always included in the syllabus of 326 every semester it's taught, and I don't think anyone's ever covered it. Now, so an eigenvector is a non-zero vector such that A times a vector is equal to this number lambda, the eigenvalue times the vector. In other words, it's when matrix vector multiplication simplifies to just scaling a vector by a constant. So what this equation is saying is x is an eigenvector of A transpose A. And finally tell you what is the closest thing I can give you to a formula for the matrix 2 norm. Yep, I'm falling behind. But once you accept that, it makes the rest of the class a lot easier. So the matrix 2 norm is the square root the largest eigenvalue of A transpose. And the square root is because everything I was working with over there was working with, my definition of g of x was the 2 norm squared. So I had to take for this. So for a given matrix, we won't be able to compute this unless it's a very simple matrix, like a triangular or diagonal matrix. So that's kind of unfortunate. But this is why we have Matlab to do such things for us. So, okay. But I at least want to give you a formula and some indication of where it comes from. And those of you who did not see eigenvalues and eigenvectors in 326, we're going to see them once in a while, not very often in this class. There is a section in Appendix B on them, but this gives the very basics, which is all we could. I would recommend, it's just a couple pages, I'd recommend taking a look at that. Okay. All right, so now there's one other matrix norm that is not induced vector norm, and thankfully a lot easier to compute. Frobenius norm. Okay. So we use a subscript f here. Is you take the sum of squares of all the matrix entries. Please do not do it again.
Sorry.
And take the square root. So much easier to compute. So it's almost like if you took the matrix and you reshaped it into a big long vector and took its 2 norm, its vector 2 norm, then that would be a Frobenius norm. Okay. So these are several different ways of measuring the magnitude of over here, a vector. Now, this is also covered today. It involves norms, so I had to explain what a vector matrix norm was. Okay. All right. I'm hoping doing this will be a lot easier in the end. Now that I've done all this, your class has been painful enough, probably. Particularly for undergrads. Okay. Conditioning of a problem solving AX equals B. And what I mean by that is how sensitive to changes in A and B. Oh, need to move this. Sorry, those of you who are watching. Okay. All right. Now, this is something I covered a lot in the previous semester for all different kinds of problems, and we're going to see any problem we talk about this semester, that there's always going to be uncertainty or input to your problem. You know, your matrix A, your vector X, or prior computation. If thrown off a lot by those errors, that's a big problem, because it means maybe we can't even trust the solution that we're getting. And there are some examples where that can happen. So we want to get a handle on if there's some error in A or B, like your input, how much could that be amplified to cause error in your output? So the idea is we use a concept I covered last semester, backward error analysis. Is error in your input. Forward error is what we really want. We want to know how inaccurate it is, but we can often estimate that in terms of error in your input. The backward error analysis. The idea behind backward error analysis is that the computed solution is the exact solution of what we informally refer to as a nearby problem. Because that assumption makes error analysis a whole lot easier. And what I mean by that in this case is A plus some perturbation times your computed solution is equal to a perturbed right-hand side. So in other words, both the matrix A and the right-hand side B are thrown off by some perturbation. So epsilon is assumed to be hopefully some small value. And the exact solution of that is the solution we compute to the original problem, AX equals B. So what that would mean is, so we want to get a handle on how much this computed solution can differ from the exact solution, X. So I'm going to use Taylor expansion. It says that X of epsilon is equal to X of 0, which is the exact solution. Because if I set epsilon equal to 0 in here, I have AX equals B. So if I have the exact solution plus, by Taylor expansion, I have X prime of 0 times epsilon plus additional terms, which I won't get into, but they're order epsilon squared. Epsilon's already assumed to be small, so epsilon squared would just be incredibly small, so we're not going to bother with it. So this right here is your amplification of backward error, because epsilon is an indication of your backward error. It's a size parameter for how much A and B are changed. So this minus this is your actual error. So it's roughly equal to the size of error in your input times this. So we need to get a handle on this. And that's a 0, not an O. I'll make clear. So if we get a handle on that, then we know how backward error is amplified to get forward error. All right. Now, actually, I can't remember if I assigned this problem or not for the next homework. Actually, I think I did, but okay. So I'm not going to go ahead and do that problem, but I will use the conclusion. Because what you can do is you can take this Taylor expansion and substitute it into here and use it to get a formula for x prime of 0. So, okay. So what you can do is, I'll give you a blueprint for that problem. So this is exploration 3.4.1. You substitute Taylor expansion, and that will be into the perturbed system over there. And simplify as much as you can using the fact that a times x of 0 is exactly equal to b. So that will simplify a little bit. And then go ahead and let epsilon go to 0. Again, after you simplify as much as you possibly can. Very important. Then you let epsilon go to 0. And what that gives you is a formula for x prime of 0. So this is the conclusion of this homework problem that you'll do later. It's times the vector E minus big E times the exact solution x. So now we're going to make use of this. So what that means is the computed exact solution is x prime of 0 epsilon plus smaller terms that we're not going to care about. Now, to get a handle on how big x prime of 0 can be, I'm going to take norms, vector norms, of both sides. Now, it doesn't matter which norm. I can use properties that apply, so I'm not going to specify one. And I'm also going to divide by the norm of, actually, instead of x is 0, I'm just going to write x. That's the exact. Then I'm going to divide by the norm of x. So what I get here is called relative error. All right, so basically I'm getting a percentage error in x. So the norm of the left side must equal the norm of the right side. So that would be absolute value of epsilon times the norm of this. But that's going to be this right here. So I'll just fill that in. A inverse E minus EX plus negligible stuff. Oh, and I'm dividing by the norm of x. I did that on the left side too. Okay. So now I have an expression for how much this input error is amplified to get my output error, but I need to simplify this, get something meaningful. Because in the last semester, we had the concept of a condition number. It's the ratio of forward error to backward error. That's what I'm after in this case. So actually, this is the condition number. I just need a more meaningful expression for it. Okay. Now, what I'm going to do is use a bunch of properties of norms. Actually, I'm going to use two properties. The sum, the norm of a sum is less than or equal to the sum of the norms. The norm of a product is less than or equal to the product of the norms. So using both those properties, I get that my relative error is less than or equal to, so I still have epsilon, and then I get the inverse that's pulled out, it's now separated. Okay. And then I have the norm of E divided by the norm of x, the norm of E, big E, times the norm of x over the norm of x, okay, plus other stuff. Okay. All right. The norms of x here. Now what I'm going to do is multiply and divide by the norm of A. So out here I'm going to have norm of A, norm of A inverse. Actually, you're going to write the epsilon over here. Let's see why in a moment. Now, in here, I'm going to have, because I multiply, I have to divide by the norm of A in here. And then over here, I have norm of big E over the norm of A. Okay. All right. So am I going to get through this in time? Oh, okay. I think I can do this. Now, using a property that the norm of a product is less than or equal to the product of the norms. Now, AX is equal to B is that the norm of B is less than or equal to norm of A times the norm of X. Now that property I'm going to use over here. Because what this means is, if I take reciprocals of both sides of this, that means that 1 over norm of A, norm of X, is less than or equal to 1 over the norm of B. So I have, okay, so epsilon, and then I have norm of little e over norm of B plus norm of big E over norm of A plus other stuff. Now, finally, I have my conclusion. This quantity here, norm of A times norm of A inverse, I call kappa, that's Greek letter, Greek K, kappa of A, and I know it's probably not a well-drawn kappa, but just go with me on this one. So this is called the condition number of A. Now, whatever norm you use leads to a different condition number. The point is you're picking some norm. Now, the thing is, you can't simplify this. A times A inverse is identity, but these are in separate norm expressions, so you can't combine them like that. Now, the condition number is greater than or equal to 1. So the larger it is, the worse it is, because this right here is a relative change in B and A. So this term times epsilon, that's a relative change in B. This here times epsilon is a relative change in A. So the relative change in the problem is multiplied by the condition number to give you an upper bound on the relative change in your solution. So if a condition number is large, like say it's 10 to the 10th power, then the tiniest error in here could still result in a humongous error in your solution. So, so when it happens, we say that the problem AX equals B is ill-conditioned. Now I actually have an example in the book, right after all this is done, where I make up a simple 2x2 matrix and a couple B's, and I show that even when B changes just by a relatively small amount, like 10%, that the solution is thrown off literally by a factor of 10 to the 7th power, or something like that, something really obnoxious like that. Now, yes, that example is kind of contrived, but the point is, it can happen. So, unfortunately, ill-conditioned systems do arise in various applications of importance, like differential equations that we'll see later on. This presents a serious problem for any methods that we use to solve AX equals B, and therefore dealing with them is a very active area of research. Okay, so often when we consider numerical methods for a given problem, we want to know not just how we can design accurate methods or efficient methods, but methods that are not too sensitive to input errors. And unfortunately, AX equals B can be extremely sensitive, and it doesn't depend on the method you use to solve it. It depends on the problem itself. It's a property of a problem. So it affects all methods considerably. So, all right. So Tuesday I will start covering. Actually, go back to section 3.3. Certain cases where Gauss elimination simplifies AX equals B. So we're a little behind, but we'll deal with it. I'll just have to give less homework or something. I know, so I should fall behind more often, right?
No.
Okay.